I actually prepared this little Python library and helps you make the setup of reinforcement learning a little bit covers. All right. No, it's not working. Okay. Oh, wrong direction. There's a message I think we can check. The quality of sound online is very bad. Okay. Then maybe I take a seat. And I hope the audio is now better. I guess it's better. Okay, then we keep it that way. I like to actually stand and move around, but I can survive for an hour. Okay, so what I'm going to be talking about today is first of all, like a tiny little introduction why active flow control is something that you might be interested in or that you should be interested in. Then second of all, I will give you like a very just very basic introduction to deep reinforcement learning, mainly to get used to some of the jargon that is often used by machine learning people, and like what it actually means in running practical simulations. Then I will show you the three different components that you need to set up your new flow control case, and how to run then a training, reinforcement learning training, and finally I will give you some more ideas and also resources that you can look at to get started with reinforcement learning. All right. So first of all, what is closed loop active flow control? In general, when you do flow control, what you would like to do is to do something like reduce the forces that are acting on your obstacle, for example, or you can also try to do the opposite. For example, if you have like a mixing process, maybe you want process intensification and you want your control basically to achieve the opposite. Something that is often interesting, aerodynamics is of course noise reduction. So in general, we decide between two different categories of flow control. The first one is the one that you are most likely familiar with, which is simply passive. So you change, for example, the shape, or you can also change in a chemical process the property of your fluid. And it's something that you do once, and you try to change it such that it's optimal for one single flow condition. Now, on the other hand side, an advantage of using active flow control is that you actually can achieve control that is not only optimal for a single design condition, but for maybe various design conditions, or even conditions that are changing, right? And examples are, like practical examples are, if you inject some mass somewhere, or if you know about hybrid laminar flow control in an aircraft, there's something called hybrid laminar flow control, where you actually try to suck out some of the mass from the boundary layer to laminarize the flow and to get some drag reduction. But it's not just like about aerodynamics. It can be also that you try to heat up some surface, or that you try to cool some surface. Of course, if you do active flow control, then you have to put some energy into your system. And in order to make it efficient, you have to be really conservative with your energy. So you have to do it very well. And within the categories of, within active flow control, there are two more categories. The first one is open loop control, which basically means I do something, I follow a constant control law. So for example, I say, okay, just suck in air with that velocity or with that kind of mass flux, for example, or take this piece and rotate it at a constant, like periodically changing, like following a sine function or something. Right? Instead of, in contrast to that, in closed loop flow control, what you try to do is actually to become more efficient by having some sensors, by looking at what the state of your system is, and then trying to act accordingly to achieve your control goal. So, for example, you will look at the pressure in certain places, maybe on some surface, And then you will try to adjust your actuation such that it's just enough to achieve your control. And the problem with closed-loop flow control is, of course, to come up with the actual control law that is actually mapping from, for example, your sensors, your pressure values, your velocity probes to the actuation. So how should I act on the current state of the system? And this is exactly the question that reinforcement learning solves. So it basically creates a so-called policy. You can also call it a control law that maps your sensor data, your pressures, and so on, to your actuation, which is angular velocity, a mass flux, heat flux, whatever. And just to show you like one motivating example, maybe, I have this benchmark case flow past cylinder. It's slightly more complex than the standard test case. So we will actually have an inflow coming from the left that varies over time. It starts at the Reynolds number of 100, and then it moves up to 400, and then it goes back down to 100. The upper row essentially shows the uncontrolled case, and in the lower row, you see an actuation that is coming from policy by control law, where the cylinder is rotated based on pressure values somewhere in the wake of the cylinder. And so at the beginning, both of these simulations look very much the same. And now you see basically the color becomes more red. So velocity increases. And at some point in the lower row, the controller kicks in and it starts to control. And as soon as we are below a certain threshold, it will stop controlling. Okay. So this is something that you can do with closed loop flow control. You're sensing what's the state of my system, and then you try to get to your goal with the minimum effort. Quickly check the question. Okay. So why do I think that like combining reinforcement learning and CFD is very interesting? So one of the drawbacks, let's say, is that typically with reinforcement learning, you need quite some trial and error iterations to learn a control law. But on the other hand side, what you can do is, first of all, if you have like something like from chemical industry where you have complex reactions, you have a safe virtual environment where you can play around with different types of actuations, right? So you don't have to have a real container of some organic material where you sparge just randomly a lot of oxygen in and see what happens, right? But you can actually do that and learn that in a CFD environment. And the second point is, of course, prior optimization. I will show actually in my talk tomorrow one of like this kind of example where you can just say, okay, potentially I have the state available in all of those points. Please tell me the top 5 points where I should sense my state in order to decide how to control it, right? So you can do some prior optimization. You can do, of course, the same with the actuation. You can say, okay, so is it better to have like 4 jets doing this control? Why should I have a rotating part? Or, you know, things like that. All right, some small, a little bit of theory about reinforcement learning, just to basically show you it's not magic, it's just some probability and gradient descent, essentially. So in general, you have 2 players in a reinforcement learning setting. The first one is the so-called agent, and the second one is the environment. In the context of CND, your environment will be like your flow simulation. So it's basically a setup of an OpenFOAM simulation and the solver that is running the setup, right? And the flow state might be basically the pressure or the velocity in a couple of points or on a surface or something like that. You get the idea. What's the agent, which is something like a Python program typically will try to do, is to manipulate the environment. So for example, by changing some boundary condition in order to achieve a certain goal. And this goal might be, for example, to reduce the forces acting on us, right? It can be also something else. And reinforcement learning terms, this is called reward. So the agent will, from the environment, receive a reward that tells the agent how well it's doing on the control objective, okay? And what the agent will then do by iteratively interacting with the environment is to learn this control law that tells you how to map sensors or states to actions. I will show you in a bit how this works in more detail. So now I have a couple of definitions, let's say. The first one is the state. This is what I already mentioned before: velocity probes, pressure probes, temperature, something like that. In general, if you think in terms of practical applications, you want S to be low dimensional because, right, if you want to control the flow past your car or your aircraft, it's not feasible if you have to know the velocity in the entire volume around your vehicle, right? Doesn't make sense. The second thing is the action. So the action is how you actually modify your simulation, how you actually, your means to actually achieve your control goal. That can be, again, that you rotate some part, that you inject some mass somewhere, or that you inject a heat flux somewhere. And for A, it's of course the same is true. You want to get away with as little actuations as possible. Then this objective that actually defines how well we are doing on our control task, this is called the reward. And for example, here, I've just written down one reward function that aims at minimizing the forces acting on the button. So the reward, this is important to know, it's always formulated such that the reward, you want to maximize the reward. So essentially, in this case, if CD goes down, right, my reward becomes larger. If CL goes down, my reward becomes larger. And of course, I can play around with different weighting factors and things like that. If you have something, some variable like CL, in this case, it would be fluctuating around 0. You probably want to take the absolute value. All right. And as I mentioned before, there will be some interaction between your agent and your environment, so your Python program and your CFD code. And with every interaction, you will generate something called the experience tuple, which is simply the tuple of state, the action that you took, the reward that you received, and the state that you transition into. Okay. Now, doing this a bunch of times, you generate something called the trajectory, which is just like an accumulation of, the pressure probe values, and the actuation that you took, so the angular velocity, for example, and then basically some function combines combining the force positions. Now the problem with fluid dynamics is that we have like a nonlinear system where the response to our actuation can be quite a bit delayed. So we cannot just look at the instantaneous reward and then decide what to do next. What we actually, and the way how this is handled in reinforcement learning is by means of a return. So we will accumulate the rewards that we receive during a trajectory, and this will be the actual target we want to control. And we will not just accumulate it, but we will introduce some kind of discounting factor, which is like just a number that is slightly smaller, typically. And what this discounting factor does is it gives the agent some sense of urgency. So, for example, if I, get a reward value of, let's say, 1.0, it will be much better to receive that reward value with very few interactions rather than many interactions, right? So if I have like many interactions, this L will be like a larger number. So you have 0.99 to a larger number, which will become like a smaller weighting factor for that reward. Okay. And this accumulated discounted rewards, or the so-called return, this is what you're actually trying to optimize in reinforcement learning. So the long-term effect of your actuation. However, there is typically some kind of uncertainty, so you cannot just work with the return directly, because it can happen because of an incomplete information of the actual state that you twice feel the same kind of pressure probes, but then you do twice the same kind of actuation, and you get two different rewards, which can simply happen because you don't have information about the state, and in practice you will never have. Okay. And this notion of including uncertainty, this is done in reinforcement learning by means of a value function. So this value function, what this value function V here tells you is, okay, say that I'm in this state ST, what do I expect from the future, right? So what is like the expected return? This is also the definition actually. And in practice, V will be a neural network. And the function that you see here, this is the loss function for this value function for this neural network. So it's a simple mean squared error loss. And now you can use that to, based on the returns you computed from your simulation, to run simple deep learning training to optimize your value network. And the value network is used. I should actually mention like what I'm explaining here is already like very close to the state-of-the-art algorithm. There are other algorithms out there, but let's say this is what is mostly used in applications that you find, and it doesn't get much more complicated than that. Okay. So what this value function is used to compute is the so-called advantage estimate, which is here simply denoted as delta t. And what the advantage estimate tells you is, let's say I'm in my current state st, and now I take some action at, and I transition into a new state st plus 1. And now I can check again what the value of this new state is to see if my situation has improved or if it has become worse. And this is why it's called advantage estimate. So in that state, taking that action, will I improve my situation? Most likely, or will it become worse? Now, what you see here, this delta t is actually like one step advantage estimate. But you could do the same with multiple steps. You could look like n steps into the future and then say, okay, after n steps, has my situation improved or has it become worse? And the combination of all these 1, 2, 3, n step advantage estimate, this is what is called the generalized advantage estimate. So just like an abbreviated version of that, the generalized advantage estimate will give you an idea, taking a certain action in a certain state, if your situation will improve in the future or it will become worse. Okay. And finally, the objective function to optimize the control law, which is the so-called policy network in reinforcement learning, where we use now the generalized advantage estimate. So I've simplified this already a little bit. There's a little bit of clipping and so on to robustify it. But essentially, what this objective function tells you is, okay, I have my policy network that gives me actually some probability distribution over actions given a certain state. And high old is the same kind of evaluation, but with an older state of my policy. Now, if my advantage estimate is positive, so if my policy, if my situation improved by taking action, I want this action to become more likely. So I want this fraction of new probability to old probability to increase, right? If my advantage estimate is negative, my situation got worse. I want this ratio to decrease. So this is this then forms the objective function for the policy network, which you can again use, optimize using standard deep learning optimization techniques. All right. Now that's it for the theory. So now comes the more relaxing part, I would say. So the problem I would like to show you how it's set up is a typical benchmark case. We have flow past cylinder at rate of sum of 100. Flow goes from the left to the right. We will have those 12 different locations where we measure the pressure. And then we will try to rotate the cylinder such that the force acting on the cylinder becomes minimum. Okay. So the way, roughly speaking, how you run a reinforcement learning training, what you have to do is essentially you will have the agent or some kind of Python program that has these networks, policy network and value network that you need to come up with the proper actuation in a given state. And you will have something that is in reinforcement learning called the buffer or replay buffer. That essentially executes multiple simulations, multiple environments in parallel. And it will use that policy or control law to generate training data. And once these simulations are done, the data comes back, you will update the networks, and you will continue the training with the improved versions of policy and Weiner with your improved control. Now, if you go to the drlFoam repository, you'll essentially find the following structure. There is like the Python package, which is simply called drlFoam. There are some examples, and there is an OpenFOAM folder that contains OpenFOAM simulation setups and source files for some boundary conditions. Within the drlFoam Python package, you have a sub-package that's called environment, which helps you to set up like a new kind of environment, so a new simulation, a new control type. You have the agent that does, this kind of learning and stuff, and you have the execution sub-package, which will take care of running like multiple simulations in parallel on the cluster and things like that. And now I want to briefly walk you through the 3 steps that you need to execute in order to set up a new control. The first one is probably the easiest one. You create a new simulation folder. So you can just create that in OpenFOAM test cases folder. In this case, this would be rotating cylinder 2D. This is like a very basic, OpenFOAM setup. What is actually particular to the reinforcement learning is that we use some function objects to retrieve the data, the states of the simulation in a couple of points. So you can use that, for example, using the probes function object. So this is going to be essentially the function object defining the state. And what's also important, these parameters here, like when to start, the control interval, and things like that. This will also determine like the interval at which you control. Okay, so everything is basically defined here in this probes function. Then, depending on your test case, you also need probably other function objects that compute your quantities of interest. In this case, we're interested in the forces acting on the cylinder. So we'll use the force coefficients function object to write out the forces acting on our cylinder patch. And finally, there should be 3 types of scripts, simple shell scripts, as you know them from setting up your OpenFOAM workflows. So the all-run.pre, this will do something like, meshing, initializing fields, and maybe, for example, run your steady state, your transient simulation, just that so that you are beyond the numerical transient that you have at the beginning, where you just have nonsensical values. So, for example, for the cylinder in the all-run.pre script, we would run the test case until we have like a quasi-steady periodic vortex shape. Then the all-run script, this will later on in the training simply execute again and again the actual simulation, so the actual code solver, and then all clean, self-explanatory, this will reset the case. That's it for the OpenFOAM test case already. The second thing that is a little bit more advanced, if you are not so familiar with coding in OpenFOAM, is implementing a new boundary condition. So the source code for this one you will find in the OpenFOAM source and then agent rotating ball velocity folder. And essentially, I would just show you what you would typically find in the update coefficient method of your class, boundary condition class. So what we do here is first, we use our function object, and we retrieve a sample of our field P and save that as a, the first one is basically just a pointer to P field, the pressure field, and then the second line of code uses the probes function object to actually retrieve the samples in the predefined points. Right? So this will be a list of our 12 pressure levels. So the next part there's a little bit of theory that I skipped over before that is necessary to understand how the agent actually explores. So the policy will actually not take your states and output one particular action, but it will output a distribution over your actions, right? So this distribution can be a normal distribution. And in the normal case, you would have, for example, mean and standard deviation that come out of your network. And then during the exploration phase, you will take this distribution and it will just sample an action, right? And what's the optimization does, it will basically optimize these distribution parameters, not the actuation itself. Okay. And there's one more thing that I need to explain. So in practice, you don't really want to use a Gaussian distribution. I just use that example because all of you know what a Gaussian distribution is, right? So in practice, like a better distribution is much more suitable because the better distribution has something that mathematicians call a compact support. So whatever I sample, I will get a value between 0 and 1, right? And this is first of all good for stability, but on the thinking practically, it's also important to not sample, mass fluxes that are close to infinity or close to negative, right? So with this kind of distribution, you can simply sample between 0 and 1, and then you rescale to the bounds that you actually prefer to have in your application, right? Okay, back to the code. So what we will do next is we will convert these p-samples into a PyTorch tensor. And we will run a forward pass through our policy network. This is what this line does, right? So what this forward pass does, it gives us a tensor from which we can extract now the distributional parameters. In the case of the beta distribution, those are sometimes called concentrations or sometimes called alpha and beta, things like that, right? And if you had multiple actuations, you would get parameters for all of those actuations. Okay, if you had 10 actuations, 10 jets you wanted to control, you would receive the parameters for 10 different distributions. Now, finally comes the distinction between what we do during training and what we do when we actually want to use the controller. So if you train, you want to explore the space of possible policies. And so what you do is you generate a sample from this distribution. So this is a little bit verbose. I will at some point refactor this a little bit, maybe put it in a parent class or something like that. Because currently in C++, in standard library, you don't have a better distribution, but you have to assemble it based on 2 different gamma distributions. It's just like a technical cycle. So during training, what we will do is we will sample our actual action, okay? And then when we actually do not want to train, when we want to exploit our control law, we will use the expected value. So the expected value for a normal function, for example, would be your mean value of this distribution, okay? For the beta, it's not the arithmetic mean. This is why it's in general called expected value. And then you will also have to rescale that back to the actual value range you would like to have. This is how this function would then be, boundary condition would then be applied in your simulation. So you take the U file, you modify the boundary for the boundary condition for the cylinder, and you specify the name of your policy, the name of your function object where you retrieve the state from, and for example, in this case, a maximum value of the angular velocity that you want to allow. So this value will be used to rescale your action. Final piece of the implementation, which is some kind of derived Python class. For this particular case, you find it in the drlFoam environment and it's called rotating cylinder. Here are just like 2 wrapper functions or convenience functions that I like to define. So if you have been following Bernhard's presentation from before, you already know if you use the read CSV function from the pandas library, you can essentially parse any OpenFOAM output that is written to your post-processing folders, right? It will be simply a single line of code calling read CSV, and you just have to, figure out the parameters, but that's like you do it once and then it's mostly the same, whatever kind of dictionary you want to read. Okay, we do that in this case for the forces and also for the probes. And then we implement the right class. So most of the actual functionality is implemented in the parent class. What we have here is essentially everything that is specific for this particular control problem. So for example, in the constructor, we take a bunch of parameters, a bunch of constants that can be simply used to change, to fiddle around with the control law. So if you want to put more emphasis, drag more emphasis on div and things like that. Okay. And the main part or most important part of this class is essentially the reward function that defines the control object. Okay, so in this case, we have some constant minus some other constant times the drag coefficient plus some other constant times the coefficient. You can now play around with that to like fine-tune your control object. So that's essentially everything you need on the implementation side. Now you can go and play around and perform a couple of trainings and see what happens. So to run a training, you go to the examples folder, and there is the Python script that is called run example that basically sets up some constants and does the actual training, not training, but like the let's say the most outer kind of optimization. So it's a very, very little code, and most of it you don't actually have to modify. There are only two pieces. So you will define in the properties of your policy and value network, what kind of activation functions you want to use, how deep you want them to be, and maybe what is missing here, like, for example, the learning rate for your policy and your value network updates. You could also define here. This is like the learning rates are, in my experience, the most important parameters. So if you have learning rates that are too high, then your optimization will. Okay. And then, of course, there's something that might be specific to your HPC environment. So you can basically create a Slurm config file here, where you specify where you want to, on which kind of resources you want to run your simulations, and if you need to load some modules and stuff like that. Finally, this is what a typical job script would look like on AWS. So this is basically now for the run example.py file, so the main driver script, which we would run, for example, using 6 CPUs, because it are six MPI tasks, because it will also do the update of the neural networks, which is not terribly expensive, but you can do it in parallel. And yes, if you actually run the script, there are a couple of parameters that you can specify: the name of the folder where you want to save your data, how many optimization loops you want to run. So this is basically the number of simulations that you execute sequentially. Then you can have something called the buffer size. So how many simulations you want to run in parallel. And minus R will be the runners. So how many simulations you want to execute in parallel in order to fill that buffer. So for example, typically you want to keep both of these values the same, but if you have like limited resources, for example, you could say, okay, I want 10 trajectories, so I want buffer size of 10, but I can only afford to have 5 runners. So you will basically have those 5 runners to do 2 loops in order to fill the buffer. Okay. And the rest is, I think, that's all right. So finally, our training is done. For this case, it will take probably like 2 hours or so. I don't know exactly the latest numbers. Now you're at the point where you have your optimized policy, which you want to try out. So what you can do to evaluate your policy is you will create a copy of the base case, which is simply like state of the simulation after executing all run free. Then you take your policy network, which is saved with file following this kind of name mentioned. You copy it into your folder where you want to run the evaluation. You set, very important, you set in the boundary condition, you set train to 0, which is equivalent to false in C++. You can also set it to false. You may want to adjust the time start, let it start earlier, let it start later. Not very important. And then you run the simulation. What you will find for this particular case, and please ignore the fact that you have multiple lines down here, just like look at any of those lines down here. Black is essentially the baseline if you don't do any control, and the other ones are different kind of policies. So if you look, for example, at the violet line here, you see the control in this case starts at 4 seconds, or in dimensionless units would be 40, and it very quickly, within about 10 time units, reduces the drag to a very small value, like 6% lower, and it keeps it there. Okay, I could now show you also how the control law looks like. It's pretty interesting, but what I decided instead to do is to actually show you what the control simulation looks like. So you see up here in the right corner, the time that is passing, and this little black line here, this will indicate you how the cylinder is actually rotating, because otherwise you would not really see it, because it's just the velocity boundary condition that's changing. All right, so let's start this. So you see we have periodic vortex shedding, simulation, and actuation starts at 4 seconds. Now you see basically how the agent is manipulating based on pressure values it finds way at the beginning a little bit more. And then it's only like manipulating the flow is very, very stable. It will only manipulate it in tiny little nudges to keep it stable. All right, that's just like because I like it. Okay. So some final remarks before before we can have a little discussion. So what I've shown you was basically focused on flow control, but actually, when you think about CFD simulations, there are many more control problems that might not be so obvious, right? So, for example, there have been some publications on turbulence modeling. Turbulence modeling is essentially a control problem. So consider your large eddy simulation where you have maybe wall function, or you have a subgrid scale model, right? And you want to, for example, know in order to match my average velocity profile that I got from my simulation, from my experiment, for example, right? So how would my subgrid scale stresses would have to look like in order to achieve this kind of average velocity profile, for example, right? So it's basically a control problem in the sense that you would need to manipulate your subgrid scale stresses over time, such that integrated over time, you get averaged over time, you get actually the right target quantity, like your mean velocity, for example, right? So just to give you one more idea. And of course, we have, when you think about linear solvers, we have a lot of degrees of freedom when you look at the multigrid solver, for example. And typically what we would do is we would set those parameters at the beginning. We hope that they are okay-ish, and then we just let them run. But of course, when you have like a transient simulation, it kind of intuitively makes sense that the solver settings that are optimal, for example, in the initial transient state, they're not necessarily going to be optimal when you reach like a quasi-steady state, for example. So like setting, for example, the parameters in your simulation, this can be also considered control. And of course, there's been also work on shape optimization. It's just the same. If you want to learn about more advanced topics, the first one is going to be like optimal sensor placement, how to put optimal sensor placement into this loop. And the second one will be about how to make it much, much faster using reduced order models. So not just learning from CFD, but using CFD data, create reduced order models, learn from the reduced order models, and then, every once in a while, skip a CFD simulation essentially to make it much faster. You are very welcome to join me tomorrow morning again. Same room actually, with air conditioning. So it's definitely worth it to come here. And we will also have a meeting of the special interest group, which takes place at the same time as all the TC and SIG meetings, and it's going to be on Thursday afternoon. And finally, I want to mention that we will have the third OpenFOAM machine learning hackathon, which takes place in about 2 weeks. And if you follow this link here, you can just register for that. Finally, I should of course mention that I haven't done all of this myself. So those names here have been students that I supervised that did one or the other work of what I showed you. Those are some participants of the last hackathons where we, essentially did debugging of drlFoam. And finally, Neil, who's from AWS, who provided us with computational resources to play around with reinforcement learning. And that's everything I have for you today. And I guess there might be some leftover questions. Yes, please. What exactly do you mean by optimal control theory? Yeah, but that there are generations. They minimize the quantities. Those data. Yeah, that's what I think I like it. So that I minimize, what's not minimize. So one alternative, maybe I can start explaining what comes to my mind, and then you can see if you converge. So for example, one alternative for this linear example could be that we use something like a PID control, right? So you would, for example, say, okay, let's take the average pressure on the left side of the cylinder and on the lower side and the upper side, and then let's try to have my typical PID terms to keep the difference at 0, right? And this would, for this example, it would also work. Okay. Now the tricky thing is, how do you extend that if you have, I don't know, like 100 actions, for example, right? Then it becomes really hard to use the PID control. That's the first point. And then the second point is, for this particular example, you can, based on basic fluid mechanical knowledge, you can define like what the state of the flow should be in order to achieve your actual control, right? So basically when my wake is essentially stabilized, then forces acting will be 0. But if you go to a more complex example, like consider an aircraft or a car, right? And you just want to say, okay, please minimize my drag coefficient, right? And you don't really have any idea about how the flow around your wing should actually look like in order to achieve that. This is something that reinforcement learning does in a better way, because you have like a more implicit way to define what your control objective is. So it's more an abstract way to define, okay, I have this black box that spits out CD and CL, and please tell me how I can manipulate my environment in order to make those become smooth. Right? And that's like the 2 points. And maybe an interesting aspect that I think is particular about reinforcement learning is the way how it combines exploration and exploitation. That is non-standard in other ways. So you essentially have this policy network, maybe, right? That first of all tells you like where you should explore, but it also tells you about how certain it is about taking a certain action, and where you should maybe explore a little bit more or a little bit less, or where you really don't need to explore much more, right? And I think this combination of function-driven exploration and simple gradient descent. I think this is something that works very well for these high-dimensional optimization problems. Okay, then we just have a chat after. Okay. Okay. Yes, please.
Shown the several magic numbers like 9, 1, 5. How setting them the situation? How do you adjust?
Okay. So let's start with this 0.99, the discount factor. This is something you never actually really change, unless, for example, actually you never change it. So it's just, and it doesn't really matter. It can be also 0.95 or 0.9. It's not terribly. Okay. Yeah, the controller that you get out of it is not something. Yes, yes. This is also, first of all, when defining these conditions, what you should take care of is that the reward you get out of the reward function has a value of whatever. This is just like to avoid having to fiddle around with other parameters like learning rates and so on. It's like a general machine learning thing. You want to keep like your values in a certain range that is typically between -1 and 1. Yes. Yeah. But that very much depends on what your control objective is. Right? So this is like your way to define in this abstract way what you want your control law to look like. Okay. So basically, if you set this value to I haven't included the plot for the lift, but essentially there will be some small fluctuations of the lift value, right? And for example, if I increase the factor in front of the lift coefficient, then maybe I get some small oscillations left in the drag, and I will drive down the oscillations in the lift to 0, for example, right? So this is your handle to actually define what your controller should do. And I mean, there's like you can set it to values between maybe 0 and maybe 1 or so. And there's not like it's not like changing over 5 orders of magnitude. So it's like, yeah, it's just like one knot that you can use to balance a little bit different quantities going into your final objective. And sometimes there's an effect of changing the numbers, and sometimes there isn't. So it very much depends on, what your optimal policy is. I mean, if you this is like, you have to at some point define what you want, right? So you cannot just say, okay, do optimal. Right? What is the game? People know what I want, but how do I know what I want in terms of this scale? Okay, like maybe let's go back to if I don't do what I think, the race would be this number, then whatever be the result. If it's meaningless, I mean, it is not meaningless. Right, it has the effect that I explained. Like if I increase, for example, right here. So if I increase this value of -0.1 to a larger number, then I will increase the importance of lift in my control objective. Okay. So if I basically, for example, let's say I skip this term entirely, right? Then what the agent will actually learn is to spin the cylinder at maximum speed, because it will actually try to divert the entire flow, right? And you could basically counteract this behavior by introducing like penalty on the energy that is consumed, right? Which is something based on the change of the angular velocity. In this case, you can also get the same effect by including the lift coefficient in your control objective. Because of course, if you spin it very quickly in one direction, it will just increase, and it will create a very large lift force. So we can we can continue chatting about that later. Yes, please. For parallel processing, there's nothing. Basically, like everything that is done in parallel is done by Slurm. So this. Yes, yeah. So basically, every simulation is decoupled from the main driver script, let's say. Yeah, I wouldn't call this necessarily a disadvantage, because actually, if like one simulation, let's say you have 10 simulations each using 10,000 cores, right? And then of course the runtime can vary because the control will vary, so your current number varies and things like that, right? And let's say like one simulation takes 2 hours and the others take 1 hour. So in that case, if you allocate all the resources once, right, you will have like 9,000 processes that will be just idle, waiting for the one simulation to finish, right? So I think like the decoupled execution of the simulations is more efficient. I don't know if they're, probably you could like circumvent that by allocating like dedicated resources for your jobs. Yes. Yeah. Yes. Yeah, I would say actually it explores too much, right? So because if you want to inject some mass, you don't want this mass flow to be, like a really large number or a really small number, right? It's much better from the engineering point of view if you can say, okay, I have my my engine, I can take that much amount of mass flux away from it, and I can use that for control, right? And then with the better function, you can just use this information to say, okay, you can control or you can inject mass in this kind of range, right? And from practical point of view, typically the better function learns much quicker than the close. So it's like a factor of maybe 2 to 10. Yeah. But on the other hand side, of course, you have to think about sensible control downs, which is one thing that at some point you definitely should think about anyhow. Like that. Yes, please. Say again, please. Yeah. Yes. So in reinforcement learning definition, like one episode is essentially one-time updating policy and value network. So the control interval, I guess that's what your question is going to be about. The control interval is specified in the probes function object. So basically you can control based on the number of time steps that has to pass or on a physical time. You could essentially, but yeah, typically this is not done. Yeah, or is it more about like the overall number of interactions between agent and environment? So for example, if you have a default simulation time of 4 physical seconds, right? And one simulation crashes for whatever reason. And in that trajectory, you only have like 5 data points instead of 100. That's fine. Not a big deal. You could have that, yes. Yeah. For practical reasons, I would say I haven't done that yet, but in general, yes, you could. Yeah. Very problem dependent, I would say. Yeah. Maybe one final question. Yes, please. Yeah. Well, first of all, I would say there are certainly many applications where, like the very slow execution time is actually fast enough. So of course, if you go like to an aircraft, right, then it's like the worst case scenario, and you need like a very quick forward pass to retrieve your control. Those are computation aspects that I think we're not ready yet to discuss. But in general, like those applications, they are very much optimized. So the libraries running the backend, right? Python, they are very much optimized, and there's dedicated hardware available. And if you have like self-driving cars, right, they do actually they process much more data in real time as you would need for this kind of application, low control application, because they have like visual data and sensors. So I think there might be some applications, some isolated applications where you would have to do some kind of pruning and numerical optimization to achieve fast enough response time. But there's a huge amount of applications that you can do right away. All right, then, yeah, 1 hour is over. I thank you for your attendance, and I hope to see some of you tomorrow.